Hey guys, it's me again, here for the problem set 4 for econometrics. I'm aware a lot of people had some difficulty, especially with the calculations on this one, so I thought I'd just sort of throw my hat into the ring. Again, disclaimer, I'm not perfect, okay? I don't know if this is right or wrong or not, okay? This is my best guess. But I did feel good about this. I've taken a bit more time to sort of make sure my answers are sort of nicely worked out and legible. So hopefully this should be a bit easier for you guys to understand. But yeah, let's get started. So, first of all, question 1. So we have the following linear regression. We have beta 0, beta 1, x1, and beta 2, x2. And we recall that the OLS estimator can be written as the estimator is equal to the actual value plus this big expression here, where R is the residual from the first stage of regression, so calculating the residual, and that is that. Suppose that MLR1 to MLR5 are satisfied, so every condition up to the normality condition is satisfied. And we want to show that the estimator minus the actual value over the standard deviation approaching of the estimator roughly asymptotically follows a normal distribution, where the standard deviation is the asymptotic variance of this, and it's given us an expression. It's also given us a few little things here. So let's go through this. First of all, we know that we want to end up with beta 1 hat minus beta 1, and we've got this expression already. So first of all, we rearrange and we get beta hat. Actually, hold on. I'm going to probably have to zoom in, aren't I? Yeah, there we go. Hopefully that makes it a little clearer. I'm definitely going to have to zoom on this one. Yeah, that's better. Maybe a little less? Actually, yeah. There we go. That's better. I've also brought up the lecture notes here, just because I referenced quite a few things from the lecture notes, so I thought that would be useful. Anyways, you rearrange it here, and you can see that the top here is what we've been given as sort of like a use without proof. So you can see the top here is essentially equivalent, so it's sort of just going to be fine. But yeah, so we can essentially replace these with this as well, and we can just put the 1 over n in because they'd cancel out on either side, so you can just put that right in and it'll work. You can add the 1 over n in before, so we replace that and we're left with this expression here. Then what we can do is that because we've got the beta 1 hat minus beta 1, we can now divide that by our expression here, and now we have what we were looking for in terms of expression on the left side, but we don't have exactly the result yet. So now we know sort of how to phrase it. We just need to work out on the right side. So we've got our expression for beta 1 hat minus beta 1, and then we've got our expression for the standard deviation here. And dividing that, we end up with this complicated mess. Okay, just hang on, and it'll be fine. Now, a crucial thing here to understand is that seeing here the residual, essentially, we want to use the law of large numbers. Now, you may have learned we learned the law. Fuck. Sorry, my throat is very. If I search up law of, if I can spell, I just said large. Law of large numbers. Yeah. So you can see it's here, and you can see that essentially as the number of observations increase, the value goes towards the expected value. So for this one, for the sample average, I think it is specifically sample average, yeah. The sample average will then tend to the expected value. So you can see here we have r squared, the sum of r squared over n, which is the sample average of r squared. So we can say that if we continue with this, it becomes the expected value of r squared, sort of like this one. So I'm also going to put these notes in the description, just if you guys want to read through them. Yeah, so we have our expression here. What we do, this is just the stages I took in. We separate out the root n from the top. Okay. we changed this to estimated value of r squared. So we changed that to estimated. We subbed out the root n. Then we times both sides by root estimated value of r squared I. So this root becomes just estimated, and we add 1 down here. We then divide both sides by root n, so the n goes away from here, and this side is now divided by n, so we're going to stick it in the root here. And now that we have 2 bits we can cancel out, both estimated values, we just cancel them, and we're left with this expression. Okay. Now, there's also the good thing about this is that, as we also looked at this week, this expression now we've got, this one, is now satisfying the central limit theorem? I forget the name. Central limit, yeah. This satisfies the central limit theorem. As you can see here, it's essentially satisfying the same thing as what we've said here. So, now that we have the central limit, and you can see here, in the central limit theorem stipulates that any standardized form is essentially going to be normally distributed asymptotically. So we now know that this expression is distributed asymptotically, and because this expression is equal to beta 1 hat minus beta 1 over the standard deviation, we can say that it's distributed normally, and that's it. Okay, at least that's as far as I got. Okay, so for B, discuss the difference between the finite sample standard deviation, standard beta 1 hat conditional on xn, that was derived earlier, and the asymptotic standard deviation introduced above. In particular, how do they compare in large samples? So, you can see, first of all, the differences between the equations themselves here. You can see that the one we had a estimated value, whereas the one here is defined with a calculated value. The difference is that you could calculate this realistically. This standard beta 1 hat conditional on xn, you could realistically calculate if you were given the samples, but this one you couldn't necessarily calculate. But the important thing here is that this standard of beta 1 hats asymptotically is going to tend to the value of calculated one as the number of observations essentially increase. Yeah, it basically, if the number of observations increases technically infinitely, these two will be identical. But yeah, essentially this one converges towards this one if you give it enough time. Okay, now for C, we are also given beta 1 hat minus beta 1 over the standard error of beta 1 hat is asymptotically distributed normally, where the standard error is the usual less standard error. Okay, so we're given this question which said, like, show that this expression is normally distributed. So we need to first of all make this into something a little more legible for us. It's raining heavily outside. I don't know if you guys can hear that, but it's raining very heavily. I kind of like it. Anyway, we want to make this into something easier. So what I've done is I separated it out into the numerator and denominator. Then you could essentially just times both sides by the standard deviation asymptotically. But I separated it out and then sort of times reverse sides. We know that this one is already this one is normally distributed. We already know that this part is normally distributed. We need to find the value of this one. So using the value of this one and then plugging in what we have been given as the formula for the standard deviation and the general formula for the standard error, we can plug these in. The sigmas cancel out, these go on top of each other, and because they both tend to the same value as the number of observations increase, the top and the bottom is identical, and it comes out as 1. So there's that. And then this is just showing that, okay, so the expression given is equal to the previous expression times 1, because that's what we found for the last one. So the expression is normally distributed, essentially. Yeah, actually, oh well. Yeah. So now for question 2. Okay, I might open stata for this. Should I open stata for this? I'm going to open stata for this. Where is the thingy? That's not it. That's not it either. Oh, fuck, I'm going to have to get it from the webpage. Where is it? It's, where? Oh, it's here. Yeah, so when you guys are doing this, you want to pick the CPS 12 dataset. So it'll load up here, and we're given the CPS dataset. Is that showing up? Yeah, it is. Okay, let's make this a little bit smaller and nicer. Yeah, I'm going to put this in this zone here, and also have to reduce the variable description site. Okay, so for the first question, it's asking us run a regression of average hourly earnings on age and report the estimated model. This is very simple. You're going to do regress or reg, if you're cool, and we're going to do AHE, which is the AHE, I got that right? Yeah, hourly earnings. So we're regressing hourly earnings against age, and then we're just going to write in age, and then you should get something that looks like this. So you should have a coefficient of 0.511871 for age, and a constant of 4.62605. That's what you should be getting. Then it asks, to report it with standard errors, R-squared and SER. I've reported it here. Just say what they are, and that's pretty much it. Or you can copy in basically the picture of the table. Basically, the question is formulated such that, at least in my perspective, you just have to say it, or at least show it. But yeah, interpret the estimated slope coefficient. So this is the effect of age on hourly wages. So we can say that with every extra year that someone gains, their hourly wage goes up by about 51 cents, given that this is measured in dollars. So, get one, it's like a birthday present. One extra year of your life, you get a 0.51 pound pay increase. Not great. Yeah. Then we have to save the residuals and plot a histogram of the sample distribution together with the best normal approximation, including the normal option. Right, let me show you how this is done. So first of all, saving the residuals is about using the predict function. You're going to have to predict, and we use, what did I do? Age, yeah. So we have to predict r underscore age r. So that's going to be the command. Predict r underscore age r. You shouldn't have anything come up. And then what we're going to do is we're going to type in histogram of r age, and then we're going to put a comma and say normal. And you should get something that looks like that. Everyone should pretty much get the same thing. That's pretty much it. And so we've got that sort of normal thing here. We also want to comment on, does that fit a normal? No, first of all, because the MLR assumption doesn't hold for this, mostly because we've omitted variables from our regression. And it often doesn't hold for cases with lots of independent factors, and especially not for cases where our R-squared is so low. What's more, that the normal distribution doesn't seem to fit it very well, mostly because a lot of the values are jutting out, and the sort of long tail doesn't really work, because you can see values above here, you can see values far above here. So the normal distribution just doesn't fit very well. That's pretty much it. So it's not reasonable to assume that the OLS estimates are drawn from a normal distribution. That's essentially what you're going to say. And justify it, yeah, you can read stuff. Pause if you want to read my work. For C, we say, use the asymptotic theory of OLS to answer this in subsequent questions. Is the estimated slope coefficient statistically significant? Well, if we look at this, we have a t-value of 11.84 and a p-value of essentially 0. So, if you remember correctly, p-values have to be smaller than the significance level. So, because our p-value is 0, it's technically going to be valid for 10%, 5%, and 1%. And that's pretty much it. So it's valid for all of them because the p-value is essentially 0. That's the deal. Construction 99% confidence interval. Oh, yeah, let me get this up. So let me get up the t-table. Ta-da! Yeah. So for a 99% confidence interval, because it's a two-tailed test is the one we're doing here, we want to use the two-tailed one, and because it's 99%, we're going to use 0.01. The critical value here is 2.576. So you're going to be using that for the multiplier to the standard error, because confidence intervals are built by the estimated coefficient plus or minus the critical value times the standard error. So you're going to do that. Here I've showed it just as the coefficient minus the critical value times the standard error, and then plus the critical value times the standard error. And you can see the standard error in your regression just here. Okay. No, I don't. Fuck off. Okay. Now the next one, 2E. Repeat A using only the data for high school graduates. Now you can make your own regressions here using conditional if statements. If statement essentially says, do this only if the data is like this. So if we want just the high school graduates, we're going to use the bachelor dummy, and it's going to equal 0. So we're going to write in reg AHE AGE, so sort of, well, age, AHE and age, like we did before, and then we're going to do the if statement, and then we're going to write bachelor, if I spell it correctly, 2 equal signs to be extra safe, equals 0. And there's our regression. You should have values like this. You should have a 0.3833268, and then you have a constant there. So that's the high school graduates one. Now it says do it for workers with a bachelor degree. So we're going to do that again, but we're essentially just going to change the bachelor from 0 to 1. Simple as butter? That doesn't work. Yeah, now we have this new regression. You can see that the coefficient and the constant is different here. So we can say, basically looking at this, that the returns to age for people who do have a bachelor's degree is a lot higher for those who do not have a bachelor's degree. So it kind of makes sense. Those with a higher education level can go on to basically command more every year, rather than those who don't have a higher education level where jobs have perhaps less progression. That could be the deal. Now for G, which is the last one, it's a little complicated, is the thing. Essentially this relies on I noted this down somewhere. It was in my book, but I don't remember where I got it. There's a expression which basically states that if two variables are independent of each other, then the variance of these two variables minus from each other is equal to the variance of them adding each other. So variance of x minus y is equal to the variance of x plus the variance of y. So using the OLS estimates in place of x and y here, because bachelor 0 and bachelor 1 are unrelated, because the data collection was not related to each other in any case here, they count, essentially. So we put them in. And because variance is also approximated by standard error squared, you can put standard error squared in here. So we use standard error squared here, and we put standard error squared here. And then to get the expression that they've given here, standard error of beta hat h1 minus beta hat b1 equals root of standard error beta hat h1 squared plus standard error beta hat b1 squared. To get that, you just root it, and then you're done, essentially. So setting up our test, we basically want to just do a t-statistic test here. So for the t-statistic, we're essentially saying that, we're seeing that is the effect different, essentially. So what you want to do is you essentially want to find the gap between them. You would essentially put minus 0 at the end of this, but it's kind of unnecessary, so I've just not included it. So this is the gap. Make sure it's the same kind of thing, but it's all right. And then we're going to calculate the standard error below as per our thing, and you should get a t-value of either positive or negative 3.294418771381. And because the magnitude of this is larger than 1.96, our critical value for the 95%, we can reject the null and say there is a difference in earnings between high school graduates and people with bachelor's degrees. Okay, I think I've done that fairly fast, so thank God. I think that's it. All right. I'll see you guys later. Hopefully I got this out at an okay enough time for some of you to do it, but hopefully that's okay. I'll put the notes in the description just because it's a little easier for you guys to maybe read through it at your own pace. But yeah, that's that. Hope every of you guys have like a nice reading week as well. Okay, bye.